Welcome, Andrei,
Thank
to
you.
this podcast. So, could you please let us know about what exact topics that motivates you to join as a research career in solar physics?
I was interested in science, in science in general, astrophysics in particular, since my childhood. So I'm going to tell you a pretty boring and standard story of a person who was all the time thinking about the same and, ended up there. So I didn't really have many twists and turns in my career. I finished my degree and then my PhD in Moscow, and then I moved to Belgium, and that's it essentially. I'm still here. Maybe a bit unusual turn was why I ended up exactly in solar physics.
Yeah.
Because of course, as a child and even maybe later as a young student, you think more about black holes, far galaxies, quasars, something which is maybe even more spectacular, let's say, because the sun is here. One can say, it's you can see it every day. One can even say it's boring.
Mhm.
I ended up in solar physics. In a sense, maybe by accident, because of my advisor. My advisor for my master thesis and then PhD. This was Professor Igor Veselovsky at Moscow University. So it's just that when I selected at my third year to study space in general, so the space plasma, and there was a quite, and still there is quite a strong group about space plasma physics in Moscow. And it just happened that Igor was looking for a student to help him in what he was doing. And I was there. I was available. I was exploring a little bit with whom I could start. So it's not that I chose the subject. I rather chose my advisor, and I never regretted that, because he turned out to be not just a wonderful advisor, but also a very nice person. That's also very important, so that one doesn't have to be only just a scientist, but also one has to have a pleasure to enjoy work with someone. So, and of course, it's impossible to be just alone. And in a sense, solar physics, I said, by accident, but not really, because this was something like 1994 or 95. And very soon after I started working with him, Soho was launched. And that, of course,
Yes.
spurred our interest. Well, it was clear this is really the top mission to study I will not say even solar physics, but the space plasma physics, of course, but application on the sun, and in particular corona. So this is, of course, what put me deep inside solar physics right away. And again, I never went out and never regretted it, because, still, even now, almost 30 years after the start of Soho, there are still plenty of interesting questions which are unsolved, and actually more new questions are getting open. So it's this is. I still think solar physics is a good choice. Is a good choice. There is we haven't heard about the switchbacks in the solar wind before Parker Solar Probe, so this is a pretty recent
Yes.
discovery. So there are still fundamental things which we have to learn about the sun, solar corona, solar wind.
In fact, I absolutely agree with you in that sense that Soho actually brings us a big platform to work in this field, because Soho is a kind of a pioneer in this field. Like, it starts a new era of its own. So I would like to know, just as an informal thing about this. So what you worked on, what project you worked on as a the start of this field, like in your masters you said that you in the masters you joined this particular field.
Of course. As
Yeah.
I said, SOHO was launched shortly after I started my master's studies. So in the beginning, what I did was trying to put some theoretical interpretation to the observations of a total solar eclipse, which were made by the group of Serge Couchemy. He was at the Institut d'Astrophysique de Paris, so the Paris Institute of Astrophysics. And they had a pretty unique observations of a small field in the solar corona. Why small? Because it was very high resolution. They observed the corona during the total solar eclipse of 1991. Well, of course, I was not yet there. They observed it from a big telescope, which was in Hawaii. It was Canada-France-Hawaii telescope. In principle, this telescope was not intended to observe the sun. This is to observe the galaxies. I think they were discovering some supernovas, not sure exactly what. But so they had to do some technical adaptations of the telescope to be able to see the solar corona. It was just a chance that the path of totality passed through Hawaii. And so the spatial resolution of the telescope was quite high, and they imaged a small field in the corona, and they saw quite some dynamic structures. There was a plasmoid, and so Serge had a long-standing collaboration with my advisor in Moscow. And so, he just gave me, he said, look, this is a cool, interesting data. Let's put some theory into it. And so, first I started to do a bit analytically, a bit numerically. And then when the SOHO data came in, it was a little bit like an avalanche. So we didn't know where to look. Well, wow, this is really great. And that is really great too. So was a bit of a free search. So I started with these eclipse observations. I actually continued. Well, in a sense, I never, my master project maybe was more focused, but in my PhD project, I was never concentrated on one subject. In my thesis, I think I had like 4 disparate chapters, so which were exploring a little bit different subjects. But this is something which gave me a bit of breadth in solar physics, so that I was ready to absorb even more new stuff after that.
That is absolutely nice. So would you like to share your first experience when you saw the eclipse? Currently you are working on coronagraph, so
my first eclipse was, my first total eclipse was disappointing.
Oh, why so?
Not because of the eclipse, but because of the weather. So this was the total solar eclipse in 1999. So we went to Romania. There was a school for young researchers, summer school. So I was a PhD student still. And it was like 40 degrees during 2 weeks of the summer school. Sun, no single cloud. Only on the day of the eclipse, when it was really morning, we had some veil of clouds, which was quite persistent. So I did see the corona, but it was very difficult to discern. We saw it just like a ring. So no big streamers. No, you couldn't. You just could guess. Probably maybe there is a streamer, but we just saw it as a ring. So in a sense, it was disappointment. Of course, it was still happy times. It was we were interacting with other students, and it was always quite interesting. And we were really it was still fun, but as an eclipse, as seeing corona, this was disappointing. Since that time, I've seen 3 more eclipses, and those ones were fine. So, and of course that was amazing experience. So I had to wait until 2006 to see the corona for real. Well, yeah, this was in Egypt, and the corona was already, well, the sun was already quite high in the sky, and of course, that's unforgettable. Although maybe the best corona I've seen was in 2019 in Argentina, because the sun was rather low above the horizon, and actually it was a bit surrealistic landscape with all these mountains. And then there is this brilliant corona, even if it was a minimal corona, minimal shaped corona, just above these mountains. This was really something unforgettable.
Yeah.
And the last one was this year in Texas. There were
US,
some
yeah, I was
clouds.
about to say.
You've been there? No?
No, unfortunately not.
Yeah, so
Yeah.
the last one was in Texas, and it was quite also cloudy, but it was clearing up at let's say long intervals of time. The sky was clearing up, and we saw the corona quite well still.
That's a really, really beautiful experience. So, yeah, so coming from the eclipse right now, so what brings your interest to the solar corona instead of other parts of the sun? Like especially the lower corona
Well,
and
maybe,
this part?
of course, a little bit what makes it exciting is that it's not really
Mhm.
readily accessible. Of course, to see
Mm.
photosphere, chromosphere, you can see it very often. And indeed, we shouldn't forget that the situation really changed only after SOHO was launched. Because before that, there was, there are ground-based coronagraphs, and there were some space coronagraphs which were operating at some intervals, the Solwind, and stuff like that. So, but still, corona was a little bit mysterious, just because, we see it so rarely. So then of course SOHO came, stereo, SDO. So now we have quite a lot of observations which we can use for our research. But I would say some of the research questions are still there. So we should be able to try to tackle them.
Yeah, especially for the lower coronal part, that part is still, I think, is not well observed. Like the upper corona, we can observe from the coronagraph, especially using the coronagraph. It's problematic to look at the lower corona because of the occulter, I guess.
Yeah, this is what is, of course, the situation which we had for a number of years, that when we could see the very low corona in EUV with imagers like EIT, later SDO AIA, and the high corona we could see indeed with LASCO C2 or stereo core 2. But indeed, what was in the middle was, there was data, but it was not satisfactory. Yeah.
So have you started like working on corona from your PhD days?
Yeah, well, in the PhD, I was already investigating quite a lot the structure of the corona and trying to associate with the magnetic field as much as we can know it from extrapolations, for example, or just from physical principles. So, and already at that time it was visible that LASCO C2 is great, and of course CIT is great, but what was in between, the LASCO C1, was not fully satisfactory because the cadence was low and the stray light seemed to be there, so it was not fully satisfactory at that time. So same one can say about stereo core 1. So it did improve on the cadence, but stereo core 1 is an internally occulted coronagraph, so that the sunlight, the light from the solar disk, first enters the telescope and then it blocks. But once it enters the telescope, it creates a lot of stray light. So this is still not the design which would be fully satisfactory to us. So when first time I heard about Proba 3, which would be creating a total solar eclipse artificially using 2 spacecraft, then of course I said, yeah, of course, that's the way to do.
Yes. Yeah. So coming to the Proba 3, could you please brief us like what are the main scientific objectives of Proba 3? And since you are a part of you are the PI of ASPIICS, so could you please brief us what are the questions you are addressing with the payload and also with the mission?
Well, the mission itself, it's first of all a formation flying demonstration. So it should demonstrate the two spacecraft flying in a very precise formation. Flying in formation means flying together. The two spacecraft would fly essentially as a rigid structure, because the distance between the two spacecraft should be like 144 meters, but the precision of alignment should be a few millimeters. So this is absolutely astonishing, and this was never done up to now. So this is still a technology demonstration. It's still, strictly speaking, well, we have to wait how this will go before we can promise good science. But our colleagues at ESA, who are making the spacecraft, they are quite confident that this should work. And so once this will work, we will be able to create our own artificial eclipses and see the corona, which would be overlapping with the fields of view of AIA on the one hand and LASCO C2 on the other hand. So this would really bring the kind of closure, the gap of our observational capabilities. So what the idea is, of course, well, as we are going to see this region of space, trying to investigate the physical processes which originate there. So first of all, to clarify maybe the structure of the corona, because it's not always obvious how the low coronal structure connects high above. Then try to investigate the physics of the solar wind, in particular slow solar wind, because we will be able to see the dynamics in the streamers. And finally, the physics of coronal mass ejection, because we will be able to see seamlessly the eruption starting from almost solar surface going into the LASCO C2 field of view. So in brief, that's it. But of course, one can talk about each of these objectives at length.
If I understand correctly, so it's basically like tracking the acceleration of the CME, like when it just emerges from the sun. Is it so, like using the corona graph? Because as far as I know that the radius is quite small compared, like it is like mostly it is focusing on the lower corona. So in that sense, is it trying to probe the acceleration of the CME?
So there are the two things. First of all is indeed to measure the kinematics. So here, the uniqueness is that, as I said, we are covering the region, which is relatively unexplored. I will not say that it's fully missing. Of course, we have seen the same region with the LASCO C1 or Stereo Core 1, or now with Solar Orbiter EY. But what would be really good is to track it without having multiple instruments, to have it from below to high above, and to have it at a high cadence. So we are planning to have, let's say, synoptic cadence of 1 minute, and during the CME Watch observation, so CME Watch is one of our programs, so we plan to have a 30-second cadence. So this would really map the acceleration very well. And the second idea is to trying to see the restructuring of the corona during the eruption. So because there are, of course, always these models like magnetic breakout, which require the multipolar, quadrupolar configuration of the coronal magnetic field, or there are models which just work without multipolar configuration, just bipolar. But unless we are talking about minimum corona, the magnetic topology in the corona can be quite complicated. And so even if it's a simple bipolar eruption from a bipolar region, It will probably somehow interact with the others. And so what we want to understand is also this restructuring, to see it directly. Of course, we can see it partially with the SDO or with the EY on board solar orbiter. So it's not that it's completely inaccessible, but there it quickly comes to the roadblock because the UV emission falls off pretty rapidly with radial distance. So it's the UV emission is proportional to the density integral along the line of sight of the density squared, and the white light is proportional to the density to the first. So it simply falls off much slower, and so it's just easier to see the evolution of the corona during CMEs in white light rather than in UV.
I have one question. So you mentioned that the spacecrafts will be like the gap between the spacecraft will be constant throughout its motion, right? But to maintain the gap will not be be very much costly in the facts of the fuel, because to maintain the gap throughout the orbit it would be like really expensive, I guess so.
So you are absolutely right, and for a moment it cannot work along the whole orbit. So the orbit of the Proba 3 is elliptical. It's a high elliptical orbit. At the closest approach, it comes like 600 kilometers above the surface of the Earth, and in the highest it's like 60,000, more than 60,000, so like almost 10 Earth radii. And indeed, to maintain the two spacecraft aligned, one has to consume the fuel. So this is why the idea of Proba 3 is to do it only around the apogee. So the apogee is the furthest part of the orbit, and during the apogee, the spacecraft are moving slower. So there is not, it's easier simply to maintain them. So out of each orbit will last 19 hours and 38 minutes. Out of each orbit, we will use only 6 hours. 6 hours around the apogee when the spacecraft move slowest. So this should give us in total 1,000 hours of formation flying and observation of the corona, which we will distribute over the 2 years of the nominal mission. So it's like observing the corona twice per week. So we will have 2 6-hour intervals every week when we will have our observation.
So another thing, so basically why you need such a strategical spacecraft, in a sense that you said that one has to be act as the occulter and the other act as the camera. So why can't we have one spacecraft with the both of the one occulter and one camera? So
this is the classical coronagraphs like LASCO C2. It's in principle the optical design of ASPIICS is very similar to the optical design of LASCO C2 or Stereo Core 2, because it's an externally occulted coronagraph. So there is an occulter. Well, in the case of LASCO, it's held by a pylon. And then there is a telescope, a little bit behind. So the distance between the entrance pupil and the occulter in LASCO, it's around 1 meter, let's say, order of magnitude. So the trick is that even if one covers the disk of the sun with the occulter disk of your coronagraph, it cannot fully kill the stray light, because there is the phenomenon which is called diffraction. So due to diffraction, the light from the solar disk, which is very bright in comparison with the corona, like 1,000,000 times brighter than the corona, it goes around the edges of the occulter and it comes in the telescope. And so the amount of the diffracted light is higher when your occulter is closer to your entrance pupil. So theory of diffraction tells us that we have to elongate further away our occulter. Well, in a sense, it's actually easy to understand, because one can consider the edge of the occulter as the source of this diffracted light. And of course, you want to put this source far away so that it's just weaker because it's far. And this is why, in a sense, the natural total solar eclipses are so efficient, because the moon, which in theory is also producing diffracted light, it's so far away. So the light, diffracted light, it's simply not visible. It's simply it's diminished because of the distance.
Like the far the occulter, the less will be the stray light, and
Yes.
the better will be the observation. So
Yes.
in a sense, then the gap you mentioned, that it's like 114 meter. So why like 114 meter? Why it's not like more than 114 meter?
Of course, to have it more than that would require even more precise formation flying. So here it's a kind of delicate balance. You want it to be far, but the further it goes, the more difficult it becomes to maintain them linked together. So you cannot just infinitely enlarge. Well, of course, there are the projects of stellar coronagraphs, which they call actually star shade. They don't call it coronagraph. When they want some very fancy petal shape occulters, they launch it, and they would launch it. It's still a project, but they would need to place it really far away. So then, either they have to do some chance alignment, let's say nearly chance alignment, or to do some even more demanding system of formation flying. So in a sense, the Proba 3 mission will open up ways not only for studies of the corona, but maybe also to studies of other things, like maybe exoplanets. So with these star shades, when it will be clear if and how this formation flying will work.
That's really, really, really interesting. So would you like to share like how like life as a PI of ASPIICS goes, like everyday life in a sense? Like what are the challenges you face as a PI of ASPIICS?
One of the maybe big challenges is that actually Proba 3, it's a small project, relatively. Well, if you compare it with missions like SOHO or Solar Orbiter, you cannot compare that. This is really an order of magnitude, at least, difference. So it's a small project, so it's a small team. So one has to be able to do a lot of things on your own. So sometimes I'm acting as administrator. I'm calculating the budgets and doing bureaucracy. Sometimes I have to go into some technical issues, like I'm trying to understand diffraction, which is not solar physics at all. I'm a solar physicist. Of course, I studied diffraction when I was at the university, but I cannot call myself a specialist on diffraction. And of course, still trying to maintain to not to forget behind all this paperwork and technical issues, not to forget why all this is done. This is all done to study the corona. So I like reading literature and trying to see what was new, and to find out what would be the new objectives which we could see. Or even here we have in our department, we have the EY instrument on solar orbiter, extreme ultraviolet imager. So I also like to work with this data and to understand. So I'm not trying to close myself in the coronagraph box. So I'm trying to have a bit wider scope. So so if you want, the main challenge is that one has to be versatile and has to do many things. Of course, for many of these things I could delegate something, because, as I said, I have a small team here. So in particular, we have a rather sophisticated software system which will be used in the SOC, Science Operations Center. So the instrument will be commanded from here. So this is also something for which, we got some funding. So we have developed this complicated system. So I have a team who are dealing with this. But all this needs to be coordinated and followed. So you cannot just say, okay, you do your stuff. Just bring me the operating software. So one has to also, I will not say you cannot become a specialist in the development of the software for this, but well, at least some notions about how this is done. I had to learn that.
Yeah, so it's basically maintaining a lot of things at the same time.
Yeah, in parallel. Yeah.
Yeah, in parallel, in versatile things. Like it's not even the same thing, like starting from the instrument to the administration. So this is a larger domains.
It's
So
it's
really,
unfortunately going in the same time. Well, okay, sometimes you just choose. You say, okay, today I want to concentrate on this and I don't want to do anything else. You can sometimes you can do it, but sometimes there are people who want your feedback regarding this or regarding that, and they cannot really wait because this will result in delays of, I don't know, some tests maybe on the spacecraft level, and there they have their own schedule which is more strict maybe than mine. So one has to do a lot of juggling of time, so the time management is it's crucial.
Time management is really, because as you mentioned, that balancing between people of various types, so that's also the crucial thing. So I just want to ask you, so when the idea of this mission actually came into the mind, like when it was the first that we have to answer such and such questions, we have to explore or address such and such questions, for that we need such a mission. So when the idea actually came?
So here it was actually maybe a bit unconventional, because we did not start with the scientific questions. So in a sense, we started from this story of a formation flying mission, which was brewing deeply in ESA already more than 20 years ago. And they had in mind applications, not just solar corona, but also there were some other missions, which would be talking about stars and maybe even galaxies. It's just it was not a linear process. Like we said, we want to study this type of science, so we need this type of instrument. It was also the process of having this formation flying mission was also brewing for quite long. And the people at ESA, they have their own objectives, what to do with this mission. They want to demonstrate not just the alignment and observations of the corona, but also a few formation flying maneuvers. Like they want to keep the alignment, but bring the spacecraft further away or closer to each other. So we would not be able to see corona during most of the time of this experiment, but they are planning to do, let's say, what they call resizing. So the distance would be changed between, let's say, 25 meters and 250 meters. So it's for them, it's while all the time being aligned.
That's really
of the formation. So this is really we should not forget that they are supposed to do it autonomously. So in principle, this formation flying, it's maintained automatically. So there is a software on the onboard computer, which, on both spacecraft, which is trying to calculate all the time which kind of adjustments it have to make. So because, of course, there will be some misalignments, the trick is to correct them as soon as possible. So actuate thrusters and to put the deviating spacecraft back to its place where it should be. So in a sense, I was not there at the very beginning of the mission, so I would not be able to tell you what came first. But of course, the questions about the corona, we knew them. We still could ask the same questions during the Soho days. And this was I think already more than 20 years ago that this mission appeared in the minds of people and the studies started. But in the same time, there were solar physicists, well, in particular in France, who noticed this and grabbed this concept, and they were pushing for coronagraph to be the instrument of this mission. And indeed, it turned out that for coronagraph, the requirements for the precision of the formation flying were, let's say, the easiest. So they, of course, they wouldn't want to start with the most difficult project. So they took something which was easier, but even this, what we call easier, as I said, well, this is the alignment precision of a few millimeters for a distance of 140 meters. So it is still a challenge. But so, yeah, this is like a little bit more than 20 years ago that it all started. And this is more or less at that time that I heard about this mission for the first time, because I had a good collaboration with the Laboratoire d'Astrophysique de Marseille. So this was, Philippe Lamy was the PI at that time. So, yeah, he told me that they are planning this mission. And of course I said, yeah, that's absolutely fantastic. Well, we will have eclipses like always, but more frequently and longer. So, yeah, of course, well, at that time, I did not know about the problem of diffraction. And so, well, of course, my enthusiasm has been tempered a little bit, but I still think it will be a fantastic mission if this will work well. And we do think it will work. So our ESA colleagues are pretty confident about this. So it was a long way because of this technology demonstration aspect. Because normally, in principle, indeed, in the science program of ESA, you come with a proposal which starts with scientific questions. You want to say, yeah, I want to study this, and this is why I need that. So in the end, we also had such a proposal at some point, but it did not come in the beginning of the mission. It came, let's say, around, I think we submitted it in 2009, when the works on the mission were already going on for a number of years, like already 5-6 years it was already being worked on. So then we formulated the proposal and we sent it. Well, it's also a little bit because of this, there is a separation in these directorates of ESA. ESA, European Space Agency, it's big and it has separate directorates. There is a science directorate and technological directorate and, a few others. So Proba 3 comes from the technological directorate. This is why I'm saying it's really, in a sense, it started with what we can do. And then we scientists saw that, this can be done. Let's grab it and do the maximum, get the maximum out of this mission.
Basically, how do you think that the Proba 3 will address the coronal heating problem?
So let's say, I would say like this. So coronal heating is maybe not our top goal, because in principle, our main observations are in white light. So we are sensitive to density. We are not that much sensitive to temperature. We have the coronal green line images. So this is the coronal like 2 million degrees, but that's it. So we do not have multi-temperature regime. We cannot really follow the heating, but I still say Proba 3 will be relevant for coronal heating because we will have observations with a very high cadence. And for a coronagraph, we will have also a very high spatial resolution. So we will be able to detect maybe the small scale phenomena like oscillations or waves, and perhaps these waves would be relevant to coronal heating, or also turbulence studies. So traditionally people are using the magnetic field measurements in the interplanetary space to measure the turbulence, the spectra, etc. We in principle could do the same with our density measurement. We are sensitive to white light, we are sensitive to density, so we can also study the evolution of the turbulence fluctuations in the corona as we see them in density. So this is also something which might be relevant to the coronal heating. So even if it's not really designed to deal with coronal heating, but I think coronal heating will be an important part of Proba 3.
So regarding this thing, so can we estimate the fluctuations in the velocity using the instrument, like or
Well,
something
as
like
I
the
said,
velocity? Yeah.
the high
Hmm.
cadence,
Hmm.
should give us the possibility to measure the velocity field in the corona. And if there will be oscillatory pattern, let's say with the right frequency, we should be able to detect it. Too high frequency, probably no. Well, as I said, we will go, well, I said 30 seconds in CMEs, but in principle, we will have a special mode when we will observe only a quarter of the field of view, and there we can go probably up to 2 seconds. And that's really, really fast because, well, SDO typical cadence, AIA typical cadence is like 12 seconds. They can go to 6 seconds. I've seen such data, but not higher than that. And with the Solar Orbiter EY, with a high resolution imager, we went down to 2 seconds also. And that data was absolutely amazing, of course, because this is really something, a very high cadence can give you a lot of information. So here, of course, our spatial resolution is significantly worse than the spatial resolution of AIA, and even more, of course, high resolution imager on EY. But due to the high cadence, we should be able still to see quite interesting things going on. So, well, as I said, these waves, the higher the cadence, the better you see them. So, of
Yes.
course,
Yeah.
yeah.
The oscillations and waves we can, yeah, like
Oscillations,
it
waves,
has
yeah.
it has really really high cadence. So yeah, in that sense, I think yeah we are expected to see the smaller fluctuations using the instrument. So when are you like planning to launch it, like estimated time frame?
So we
So
have now a launch date. So the launch date
mhm.
is 4 December of this year. So yeah,
Big
so
day.
this very
Yeah.
we are very excited. The spacecraft are already at the launch base, so it will be launched from India, so from Sriharikota, and the spacecraft were transferred there already, well, like 10 days ago, and they started making all kind of tests. And for a moment, everything is going nominal. We do not expect any obstacles. Well, of course, there is still a number of tests to be run, and then the fueling and well, fitting into the launcher. And so this will still take, well, a bigger part of these remaining 3 weeks. But yeah, it's after so many years of working and
Yeah,
waiting and working and waiting, finally saying that we are launching in 3 weeks, this sounds unreal.
that's a big day. So like yeah, so from another perspectives, that so how do you see that this particular mission will change the next few years of coronal observation and the course of heliophysics, the course of
Well,
solar astrophysics?
I
Yeah.
do hope for an immediate impact. Well, we will have the first coronal images in 4 months, something like this, after the launch, because there should be commissioning and all kind of tests after the launch. But well, immediate impact, as I said, is that this will give a new data set of a region which is underexplored. I will not say unexplored, because there are, of course, the attempts to observe this coronal region from the UV imagers. But of course, well, this region remains underexplored. So I do hope for more studies of CMEs and more studies of the solar wind, but also more cooperative studies, because of course we should be able to act in concert with the other space missions which are already there, like Solar Orbiter or Parker Solar Probe. So things can be done together with them. So if you want, I would not say that Proba 3 would single-handedly change the course of solar physics, but it will add an important piece in the puzzle which is different missions, different data sets are putting together. So this would be, let's say, the short term. And on the long term, I do expect that other new space missions would want to use the concept of formation flying, not only for coronagraphs, but for example, a number of years ago, there was a project of a space mission to observe hard X-rays from the corona, from flares. And they had, I think, X-ray mirror on one spacecraft and detector on the other. So the grazing incidence. So this would take. It would be very useful for them to have this system separated on two spacecraft. Or the other thing was, another idea was to launch what is called a photon sieve. So this is a specifically arranged instrument. Well, it's looking like a sieve indeed. It's a circle with many holes arranged and sized in a special way. And the interferometric pattern from this gives a very high resolution for the UV. But for this, one also needs this to be separated from the telescope, from the detector. So, there might be, and as I said, it's not limited to solar physics. There might be other, like exoplanetary missions, which would want to use this concept of formation flying. So I think the future is bright.
Yeah, indeed. So is there any particular reason to launch it in this particular timing, like solar maximum, or it can be, it's not a particular reason?
I would say here we were purely driven by the instrument and spacecraft development schedule. So essentially we are launching when we are ready. We should have launched before, but the COVID pandemic slowed us down significantly. And this really, it took time to recover and to finish this. The work never stopped, but it became significantly slower. So there were additional delays introduced. So to be honest, I would maybe prefer we would be launched in the, let's say, well into the rising phase of activity. Why? Because, our original plan was actually to launch at the minimum. So the idea was that during the first year, when the activity is really low, we exercise simple observations, like 1 minute cadence, so something which is not so challenging. But on the second year, when we will have more CMEs, then we really push our instrument to its extreme and to try to squeeze out the most of it. Now it seems we will have to start with the challenging observations,
Yes.
start with CME observations, which are really will push our instrument to its limits. And only then, maybe in the end, when the activity will be calmed down, then we will run our more, let's say, relaxed programs. But in a sense, it's good because the CMEs are right there. Because, of course, it's also challenging to catch them. We will not be able to catch all of them. It's to a big extent, it will be by chance. Because, as I said, we are observing twice per week by 6 hours, so we will have 12 hours observations per week. But of course, we will try to do our best to time the observations. We can. There is a bit of flexibility. We can try to observe 3-4 times per week if we feel that there is a good active region which is producing a lot of CMEs. So this is also the part of the operational work that we have to know when to observe, even if we cannot predict and to say, yes, the CME will happen on this day we want to observe. No, but at least we can put more observing time when there is a good active region. So we do hope to catch many CMEs.
And the other thing is that we know that when the CMEs are really fast, they drive shocks. So can Proba 3 see a shock?
Yeah, because we know that in LASCO C2 has seen many shocks. There should be no particular reason why we should not, except maybe that we are still looking very low. So if the CME is accelerating slowly, will not have time yet to reach the speed which would be enough to drive the shock. But for very fast CMEs, which are really starting very fast, we should be able to see them. We should be able to see the shocks for the fast CME.
Yes, exactly. And so it is a kind of a general question I'm coming to. So how do the mission connects to the space weather?
So I would say, well, okay, this is clear that Proba 3 is not a space weather monitoring mission. We have no capability like SDO AIA to observe the sun all the time and transmit the data quickly in real time. This is not possible. Sometimes we will have serious data latency because we actually can have more data on board than what we can transmit to the ground. So we will have to be selective, and well, the telemetry is not, let's say, sufficient. So it will take sometimes weeks before we get the data. So from the point of view of space weather monitoring, we will not have an impact. However, what we will definitely do for space weather, we will help to understand the process of CMEs, how the CMEs are originating, to try to understand the physics, which will hopefully one day help the community to come closer to the problem of the CME prediction. And well, if we contribute, even as I said, a small piece of puzzle into this, which would allow us to sooner or later predict CMEs, I would be very happy.
Yeah, so in that sense, it would be really contributing into the CME forecasting, because we will be knowing more into the system, into the CME thing. What do you think, according to you, except for the coronal heating problem, what are the other unanswered problems in the domain of solar corona that one can try to look or try to probe?
So I briefly mentioned before the slow solar wind. So let's say for the fast solar wind, I would say the knowledge is relatively well established, that it comes from coronal holes, and well, but although even there are still questions. But about the slow solar wind, there are a few theories or models which do link the variability of the slow solar wind to the small scale dynamics in the streamer belt, and in particular at the cusps of the streamers. So like interchange reconnection, the formation of plasmoids, the interaction between the open closed field lines. So we do know, again from LASCO days, LASCO C2, that there are these blobs. This was the paper by Neil Shealy, which are, let's say, tracers of the slow solar wind. So we want to see these blobs at a higher cadence, at a higher resolution, to measure them more, to try to understand how these blobs, or maybe some other similar structures. Well, there were, of course, observations in the recent years from other instruments which deepened this understanding. We want to see in detail how these structures are formed and how these dynamics in the cusp region is affecting the process generating the slow solar wind.
Absolutely agree with you in this thing. So another small question. So can the corona graph currently in its current position, can it also monitor the rotation of a CME?
Well, for sure, we can see the deflection when we have a CME originating, let's say, from the higher latitudes and then being deflected towards the equator. This we should see pretty easily. Mm-hmm. For rotation, it's maybe not so straightforward, because our field of view is limited and the CME rotation is rather slow. So it's not going on too fast. But we will certainly see the erupting prominences associated with the CMEs. And sometimes, indeed, these prominences are doing pretty weird things, which can be interpreted as rotation. So yes, we should be able to see some of these effects too.
So you have mentioned about the solar wind, the slow solar wind, and the open questions in this aspect. So, what do you think are the most important challenges to probe those aspects, to answer or to address those things?
Yeah, in general, I'm perhaps a bit biased, but of course, I would say it's the accessibility of the cusp region. So you usually do not see the cusps in AIA observations. The cusps are higher. And in LASCO C2, the structures are very bright, close to the edge field of view, so the cusps are probably lower. So you want to see that in more detail. So yes, of course, there are now the observations with Solar Orbiter Pulsar Imager or with SUVI. There were publications which were tracking the dynamics in these regions. So this is, of course, very important. But as I said, well, in UV, it's still challenging because the intensity falls off very rapidly. And then it's challenging to have a cadence. In principle, with EUI, with Solar Orbiter EUI instruments, we have the occulted mode. So even if it's not a true coronagraph, we can occult the sun and then have the corona imaged up to a few solar radii. So so it can go quite far. Unfortunately, there the exposure times are of the order of 1,000 seconds. So it's 15 minutes. So all the dynamics which you have during this time is somewhat snared. We do see CMEs, propagating, but they look a little bit more diffuse than what we are used to with LASCO C2. So I would say that you want to observe this region in white light with a good cadence to track the dynamics better.
Yes. Another just a general thing. So because we are in the end of our podcast, almost the end of our podcast. So if not to be an astrophysicist, a solar astrophysicist, what else would you like to be?
As I said, I was dreaming about being an astrophysicist since I was a kid. So I would become then another type of astrophysicist, maybe not solar.
Okay.
There is a lot of interesting observations now about the cosmology. The James Webb Space Telescope, it's seeing so many amazing things very far away from the Earth. I would be happy to study those. So I'm wishing these guys a lot of success in these things. I'm still trying to follow a little bit the major achievements in astrophysics. So just, in my free time, of course, I'm not a specialist at all in this type of science, but it still feels nice when you see, they discovered the farthest galaxy ever observed, that Z equals, who knows what, I don't know, 12 already maybe. So, or they saw some star formation, or let's say the gravitational waves. That was the major discovery. That's there is a lot of things going on in astrophysics too. So if not solar astrophysics, maybe some extragalactic astrophysics would be very interesting too.
What would be what would you like to suggest for the future solar astrophysics?
I would say at this time it's important to remember that one should not give up, because sometimes PhD takes so many years. One has to work, sometimes work a lot. So not to give up, just pursue. To talk to your advisor if you feel in trouble. Don't be shy about that. And I think the efforts in science are usually rewarded. So a little bit of persistence definitely helps. But if you just honestly work, I think this is an amazing time in solar physics, and not only. There is always something new in science. If again not in solar physics, it may be something else. So if there is a funding for this, one can work. So isn't it the best job in the world? You are paid just to satisfy your curiosity.
Yes. Many thanks. And for the, I guess, the final question. So looking like at this stage, looking back at your own life, what do you think that the most important inspiration for you to like pursue your field in this particular field, like in this particular subject?
I still think one of the biggest aspirations was that I met so many amazing people, starting from my master and PhD advisor, Igor Veselovsky, continuing with Serge Kuchmy and then Philippe Lamy and many other people who I met and learned from on this way. So it was an amazing experience, and when you see how hard these people work, how creative they are, you just want to follow. You just want to follow.
Thank you. Thanks a lot, Andrei. Thanks a lot to be like in this podcast. And
Thank
I'm
you for
really,
inviting
really
me here.